Today's topic is Mazur's Chapter 4, Momentum. This time, I think you should skim Mazur's Chapter 4 and really focus on the concepts half. Don't worry so much about the equations. See if you can do some of the checkpoints. I'd eventually like to make this video lecture self-contained so you don't have to read the book, but I like Mazur's Chapter 4 so much that I don't really think I could discuss it nearly as effectively at this point unless you've at least skimmed through it to see the ideas. The slides I show in today's video are linked from the Canvas assignment and from the comments at the bottom of the video. phys0008slides04.pdf. Momentum is the product of mass m and velocity v. Velocity is a vector. Mass is a scalar. When you multiply a scalar by a vector, you get another vector. So the product of mass and velocity is a vector which we label p, the vector momentum. So momentum is mass times velocity. Momentum is a vector. Velocity is a vector. We, for the first 9 chapters of the book, are dealing only with the x-axis. So we will worry only about the x component of momentum. So we'll say that p sub x, that's the momentum in the x direction, equals the mass times v sub x. This is the velocity in the x direction. So the x component of momentum equals the mass times the x component of velocity. By the way, chapter 4 will use the word inertia to refer to m. It's a little bit confusing, especially since m makes you think mass. The reason why chapter 4 so scrupulously uses the word inertia instead of the word mass when writing the symbol m is that mass plays 2 roles in physics. One role that mass plays is how much an object is attracted by gravity. The strength with which Earth attracts you gravitationally is proportional to your mass. It's also proportional to Earth's mass. The other function that mass plays in physics is that the more massive an object is, the more difficult it is to accelerate, the more difficult it is to change its velocity. The second property of mass, that the more massive an object is, the more difficult it is to accelerate it, the more difficult it is to change its velocity, that property of mass is called inertia. When referring to how the fact that it's more difficult to make more stuff change its velocity than it is to make less stuff change its velocity, Mazur uses the word inertia, even though it's the same letter m. I will say mass because I've learned over the years that it's more natural for you if I just say mass. But in the context of momentum, you want to bear in mind that the role that mass plays is that role of inertia. So inertia is the same thing as mass. Inertia is mass. But in particular, when we refer to inertia and we refer to mass in the context of momentum, we're referring to the fact that it is more difficult to accelerate an object which is more massive. You have to push harder on something which is more massive to get the same change in velocity. The reason we're talking about momentum is that momentum is a conserved quantity. This is a hugely important idea in physics, the idea of a conserved quantity. A conserved quantity can be transferred from one object to another, but it can never be created or destroyed. A conserved quantity is something that can never be created or destroyed. It can be transferred from one thing to another, but it can't appear out of nowhere or disappear into nowhere. Maybe a more familiar idea from everyday life is sort of the idea of money collected among several bank accounts. Maybe you have a savings account and a checking account, and let's assume there's no monthly interest and there's no monthly fee. Unless you somehow externally put money in or externally take money out, you know that the total quantity of money should stay constant. And maybe you shuffle things back and forth between your checking account and your savings account, but still the total stays the same. A conserved quantity allows us to use this really useful bookkeeping device that says, well, as long as I can draw a line around somehow this system. Actually, system is another really important concept that's going to be useful when using conserved quantities. So, you have your 2 bank accounts, and you can say, well, let's say the system consisting of my checking account plus my savings account. There might be flow back and forth between savings and checking of money, but let's say there's no money going in or no money going out unless I explicitly make a transaction of that sort. So then if I define this system, then I can say that the total money in this system is conserved. Okay, so momentum is a conserved quantity, and if you're able to define a system such that you know that no momentum enters or exits that system externally, you can say that the total momentum of that system is constant. In particular, if we isolate a system so that that system is not pushing on or pulling on anything outside of the system, then the momentum of that system as a whole is constant. So if objects within a given system, maybe they push on each other or pull on each other, but they do not push or pull on anything outside of the system, then that's called an isolated system, and the momentum of an isolated system is constant. So that's going to be extremely useful because it then allows us to do momentum bookkeeping. Let's just look really quickly at an example of momentum being transferred from one object to another. And then let's just look really quickly at an example of 2 objects interacting with one another in such a way that you can see that the total momentum afterward is the same as the total momentum beforehand. So you can see that one of the 2 objects will gain momentum going this way, one of the 2 objects will gain momentum going this way because they push on each other, but the total momentum of the 2 objects is the same before and after their interaction with each other. So momentum is mass times velocity. Why is that factor of m there? It's because imagine throwing a baseball and then imagine throwing a heavy medicine ball. And you know that you will tend to recoil much more from throwing a heavy medicine ball than from throwing a baseball. Somehow it takes you much more effort. You have to push much harder to change the velocity of a heavy medicine ball than you do to change the velocity of a relatively lightweight baseball. Now, when you think about that, it's somewhat complicated by the fact that not only are you pushing on the medicine ball, but also the ground is pushing on you. When you throw the medicine ball, you're interacting with the medicine ball, but you're also interacting with the ground. The contact of your rubber shoes with the ground will prevent you from recoiling. And you can see in the video clip in just a second, Mary and me throwing a medicine ball back and forth, first when we're both wearing rubber-soled shoes, so each of us has good contact with the floor of the auditorium, so then it's not easy to identify any isolated system, so then you don't see the expected recoil. Then we will see what happens when Mary puts on roller skates. So then when Mary throws the ball, from the instant before she throws the ball until the instant after she throws the ball, the system consisting of Mary plus the ball is isolated because Mary is only pushing on the ball and only the ball is pushing on Mary. There's no interaction with the ground to worry about. So then you'll see when Mary throws the ball toward me, she recoils. A short time later, you'll see that when Mary catches the ball after I throw it back to her, she recoils again, and then she'll throw the ball back to me and you'll see her recoil again. So whether Mary catches or throws the ball, you will see her recoil because there's no interaction with the ground to stop her from recoiling. Each one of these throwing or catching events demonstrates this idea that the momentum of the ball plus Mary system just before the throw or just before the catch is the same as the momentum of the ball plus Mary system just after the throw or just after the catch. Just imagine what it feels like to throw a heavy medicine ball. Now imagine doing the same thing while standing on a sheet of ice. Okay. Another word you'll see in chapter 4 is impulse. The definition Eric Mazur uses for impulse is a transfer of momentum from outside of a system to inside the system, or from inside the system to outside the system. So a transfer of momentum across a system boundary is what Eric calls impulse. So impulse is sort of like a bank transaction from outside or inside your bank account. It's something that can change your bank balance. So if you do draw a nice boundary around a system, if you can eliminate all possible exchanges of momentum between that system and the outside of that system, you say that momentum is constant for the system. If you can't say that, then you attribute the change in the system's momentum to some impulse. So the impulse is a transfer of momentum into or out of a system due to interactions with something outside of the system. If you watch me throwing and catching the ball in that clip, if you take the ball plus me system, its momentum is not constant. You notice that the ball is moving toward me, I catch it, and then after I catch it, nothing is moving. So somehow, just before I catch the ball, there is net momentum toward me, and just after I catch the ball, there's zero net momentum of me and the ball together. And that's because there's some external influence of the ground which is preventing me from recoiling. So that transfer of momentum from the ground to the ball plus me system is an impulse. So we'll use impulse as a bookkeeping mechanism to account for the possibility that momentum enters the system or leaves the system from outside. But most commonly, we will consider the case where there is no impulse, there is no interaction with anything outside of the system. We'll consider an isolated system. We'll consider a system whose parts interact only with each other. So if there are two objects, and usually our system will just have two objects in it. We'll have two objects in a system, and they only push on each other, or they only pull on each other. And that means that the total momentum of the system before they interact is the same as the total momentum of the system after they interact. And that lets us do bookkeeping. So imagine a scenario where initially we have object 1 moving to the right and object 2 standing still. And here's the little clock at midnight. And then later, here's the little clock at 4 p.m., let's say. And later we have object 1 standing still and object 2 moving to the right. And let's say object 1 and object 2 interact only with each other. So they form an isolated system. So they might push on each other, but nothing outside that 1 plus 2 system is pushing on anything inside that 1 plus 2 system. So here's our initial state, and here's our final state. We can say that the total momentum of the initial state is the total momentum of the final state. How do we write that more carefully? First of all, let's just use x components. Let's also say the momentum is the momentum of cart 1 plus the momentum of cart 2. Then we will say P1x initial plus P2x initial equals P1x final plus P2x final. Momentum is mass times velocity. So then we can go one more step and we can say m1 times v1x initial plus m2 times v2x initial is m1 times v1x final plus m2 plus m2 times v2x final. This looks like a little bit of a mess. It's much easier to talk about changes in velocity of one cart and the other cart. As a matter of fact, there are a couple things we can say here. One is that P1x final minus P1x initial equals the opposite of P2x final minus P2x initial. So that's the same thing as saying delta P1x equals minus delta P2x. x. That's saying if object 1 gains momentum, then object 2 must lose the exact same momentum. If object 1 loses momentum, object 2 must gain that same amount of momentum, so that the change in one momentum is the opposite of the change of the other momentum. In other words, the sum of the two momenta has to be unchanged. What's the implication for changes in velocity? Well, we'll see that we have m1 times v1x final minus v1x initial is the opposite of m2 times v2x final minus v2x initial. Another way to write that is m1 times delta v1x is opposite of m2 times delta v2x. We can summarize that in a way that's easier when you're watching things collide on a track by saying that the change in v1x divided by the change in v2x is minus m2 over m1. So if you see two carts of different masses collide on a track, the more massive one will have a smaller change in velocity. The less massive one will have a larger change in velocity. Each change in velocity will be inversely proportional to the corresponding mass. And if the change in object 1's velocity is to the left, then the change in object 2's velocity will be to the right. So we're going to see this in some examples of two carts colliding on a track right now. We're going to see large numbers of examples of problems where we have two things heading toward each other, or one is heading toward the other, which is stationary, and you know what's happening beforehand, and you want somehow to predict what's going to happen afterwards. We're almost always going somehow to reason that the system must be isolated. I mean, there might be some cases where you can argue why it's not, but you sort of argue why is it that you can understand that the two objects are interacting only with each other and not with anything else. So that lets you then draw some nice system boundary around the two objects, and then you say the system is isolated. And if you're solving a problem with equations, we will almost always write down m1 v1x initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. Again, we like to imbue equations with meaning. We don't just like to write down equations. What does this mean? Momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. What does that really mean? Total momentum of the system before they collide equals the total momentum of the system after they collide. Kind of like money in the bank, momentum is a quantity where you combine two things, you can add up what's inside them both. So you add up the total momentum of the two constituents of the system before, and you say, well, that must be the same as the total momentum of the two constituents of the system after, as long as you're able to argue that the system is isolated so that you know no momentum flows in or out of the system, which you can then argue on the basis of nothing outside the system is pushing on or pulling on anything inside the system. Now, when we watch things on video colliding on the track, there's a much more intuitive way to look at this that aids the eye. You see, when these two things collide, object number 1 is going to experience delta V1 in that direction, and then object 2 is going to experience some kind of delta V2 in that direction. And it's not the delta V's that are going to be equal and opposite, but it's going to be the delta P's that are equal and opposite. If they're the same mass, then their delta V's will be equal and opposite. But if they're in general, they'll be different masses. So it's really their changes in momentum that will be equal and opposite. If you have the x-axis pointing this way, then probably object 1 will experience a change in velocity whose x-component is negative. Object 2 will experience a change in velocity whose x-component is positive. And you want to compare those two things. You say, how does delta V1 compare with delta V2? The minus sign tells you that if object 1 experiences a change in velocity to the left, then object 2 must experience a change in velocity to the right, or vice versa. And this ratio tells you that the more massive object will experience a smaller magnitude change in velocity, and the less massive object will experience a larger magnitude change in velocity. So let's look at that again. Okay, let's watch some examples of a blue cart and a red cart colliding on a little horizontal track, and each cart has little wheels whose purpose is to make the rolling of each cart relatively frictionless. Then we're going to envision that the two carts are interacting only with each other and not with anything else from the instant before the collision until the instant after the collision. And in the first case, the two carts will be the same mass. So the blue cart will have the same mass as the red cart. And the first example, the blue cart is moving to the right initially, and the red cart is stationary. Since we're having the x-axis point to the right, v1x initial is positive and v2x initial is 0. 0 velocity means stationary. Positive velocity means moving to the right. After the collision, we'll see, in this particular case, v1x final is 0, v2x final is bigger than 0. In other words, what you'll see is that cart 1 after the collision is stationary and cart 2 after the collision is traveling to the right. What does that imply for each change in velocity? Delta v1x is v1x final minus v1x initial. So 0 minus positive is negative, so delta v1x is negative. What does that mean? It means its change points to the left, and that will make sense because it starts out going to the right and then it stops. So what is a change in its velocity? That is a left-pointing change in velocity. Meanwhile, the red cart will start out stationary and end up going to the right, so that is a positive change in velocity, the x component, because positive minus 0 is positive. So delta v2x will be positive. So we'll have delta v1x is negative, delta v2x is positive, and they'll be opposite each other because the ratio of the two masses is 1. So if v1 experiences a positive change in velocity, then v2 experiences a negative change in velocity of the same magnitude as long as the masses are the same. Let's watch that. The next scenario we're going to watch on the little track is the same two carts, equal masses, but the blue cart will be moving to the right, the red cart will be moving to the left, and then they're going to collide, and after they collide, you will see the blue cart moving to the left and the red cart moving to the right. So initially, blue is moving to the right, red is moving to the left, and then when they're all done and they finish colliding, afterwards, in the final state where Mazur's book would show like a clock at 4 p.m., you're going to see the blue cart going to the left, the red cart going to the right. So what does that mean? This is final minus initial. Final is negative, initial is positive, the x-coordinate. Here, final is positive, initial is negative, the x-coordinate. Negative minus positive is a negative change. Positive minus negative is a positive change. So delta Vx of the blue cart points to the left, delta Vx of the red cart points to the right. Because their masses are the same, those two changes in velocity have the same magnitude. So if the blue cart recoils to the left with 1 unit of change in velocity, then the red cart recoils to the right with 1 unit of change in velocity. Let's watch that. Okay, now let's change the assumption that the two masses are the same. The way we're going to do that is we'll stick a little brick into cart 1 such that we effectively double the mass of cart 1. So now the mass of cart 1 is 2 times the mass of cart 2. Okay, so cart 1 has 2 units of mass, cart 2 still has 1 unit of mass. And let's start out in the initial state with cart 1, the blue cart, moving to the right, and cart 2, the red cart, stationary, minding its own business. So here's initial with a little clock, kind of close to midnight. Here's final with the little clock, kind of like at 4 p.m. So after the collision, we will see the blue cart, cart 1, moving to the right still, but with a smaller velocity. Goes from moving to the right a lot to moving to the right a little. Then we'll see the red cart goes shooting off to the right with a pretty big velocity. Remember, delta v1x over delta v2x is minus m2 over m1. So that's minus 1/2 if m1 equals 2m2. So delta v1x, therefore, should be minus 1/2 of delta v2x. So we could also say that minus 2 delta v1x should equal delta v2x. Afterward, v1x final is greater than 0 but smaller. The v2x is bigger than 0 and it's pretty big. If you take this arrow minus this arrow, this is final, here's initial, delta v1 points this way. So you take this arrow minus nothing, that is a pretty big arrow that way. So here's delta v2x. So you see delta v2x is bigger than delta v1x, and they point in opposite directions. So the red cart experiences a change to the right, which is big. The blue cart experiences a change to the left, which is small. It's only half as big a change in magnitude. Let's watch that. Okay, let's collide the same two carts. The blue cart has twice the mass of the red cart. So blue cart, 2 units of mass, red cart, 1 unit of mass. But now in the initial state where the little clock is close to midnight, we will see the red cart moving to the left and the blue cart stationary. So in the initial state, the blue cart has an x velocity of 0 and the red cart has an x component of velocity which is negative. And then what we're going to see is that after the collision, the red cart will be moving this direction. So this will be bigger than 0. And the blue cart will be moving to the left with a pretty small magnitude, but it'll be moving, here's less than 0, but this is going to be small, and this is going to be going to the right, and it's, well, I guess it's medium size. So then afterwards, the blue cart is something like that. To go from nothing to pointing this way is a change, which points this way. And to go from this way to that way is a change, which points that way. And going from this way to that way is a bigger change than going from nothing to that way if these two things are similar in magnitude. So you're going to see the change in velocity of the red cart is twice as big in magnitude as the change in velocity of the blue cart. But notice that the change in velocity of the blue cart points to the left. The change in velocity of the red cart points to the right. See if you can see that. Because for the blue cart, initial is stationary, final is to the left. So to the left minus stationary is a change which points to the left. For the red cart, initial points to the left and final points to the right. Right minus left is a big change to the right. The change in velocity for the red cart is a big arrow to the right. The change in velocity for the blue cart is a small arrow, half the magnitude, to the left. Let's watch that. Go this way. The next scenario we're going to watch, so the same two carts. So blue cart has 2 units of mass, red cart has 1 unit of mass. Now they're going to be moving toward each other with comparable speed, but it's kind of like a small truck moving toward a car. The truck is more massive than the car. So they're moving toward one another at comparable speed, but of course the blue cart will have a bigger momentum than the red cart in the initial state. So V1x initial is positive, the blue cart's moving to the right. V2x initial is negative, the red cart initially is moving to the left. After the collision, we will see the blue cart moving to the left, but at a small speed, and we'll see the red cart moving to the right, but at a big speed. I have a little blue arrow going to the left for the final state, and I have a big red arrow moving to the right for the final state. If you subtract, so I take the final blue state minus the initial blue state, take this arrow minus this arrow minus that arrow. If I turn that arrow around, then I get something that points like that. By comparison, let's say I take this arrow minus that arrow, so I want to subtract that arrow, I turn that arrow around, then I get something that's kind of like this. That kind of makes sense. Here is a big delta V2 to the right, and here's a small delta V1 to the left, because the ratio of the two magnitudes should be a factor of 2. The less massive vehicle should get the bigger change in velocity. The car should have a bigger change in velocity than the truck if a truck collides with a car. They're moving toward one another, so they both recoil, but the change in velocity of the 1 unit of mass is bigger than the change in velocity of the 2 units of mass. The way we understand that is each one experiences the change in momentum of the same magnitude, because this is a big mass times a small change in velocity, and this is a small mass times a big change in velocity. So those two changes in momentum are equal and opposite. They add up to 0, but what your eye sees is the changes in velocity, and you see that the red cart experiences a large change in velocity to the right, the blue cart experiences a small change in velocity to the left. This is when they start out moving toward one another at comparable speeds. Let's watch that now. For the next little segment, we're going to stack yet another little block of mass onto the blue cart. So the blue cart will have 1, 2, 3 units of mass, and the red cart will still be just 1 unit of mass. M1, here's 2. So M1 is 3 times as big as M2. So our first little experiment will have the blue cart moving to the right and the red cart stationary. So V1x initial is positive because positive x-axis is to the right, and V2x initial is 0. So that is 0, and that is moving to the right. So this is a little bit like a moving truck hitting a stationary car where nobody is stepping on the brakes, except that the mass ratio now is even bigger. So the change in velocity of cart 2 will be 3 times the magnitude of the change of velocity of cart 1. After the collision, cart 1 will be moving forward, but it'll be moving forward less quickly, and cart 2 will be moving forward very quickly. What does that look like for a change? So if you take final minus initial, negate the initial state so we reverse its direction, final minus initial, and that looks like a change that points this way, and so it's like pointing to the left, but it's not too big. And then if we take final minus initial for number 2, so final is a big arrow to the right, initial is nothing, so this is a big change to the right. So we have delta V2 is a big change to the right, and delta V1 is a little change to the left. In fact, this change to the left is 1/3 as big as this big change to the right. Let's see what that looks like. Okay, the next thing we're going to look at, same ratio of masses, 3 units in blue, 1 unit in red. Let's have the blue cart stationary, that means Vx initial equals 0. And let's have the red cart moving to the left, so that means Vx2 initial is less than 0. So this is kind of like a lightweight car colliding into a truck. In this case, we've set things up so it's like they both have really springy bumpers and nobody's stepping on the brakes. So we're going to see the little car recoil from the truck, but the truck will also recoil a little bit because it's pretty massive. Vx1 final will be to the left, so it's negative, but small. And then we'll see V2x final will be to the right, but big. In the final state, we'll have the blue cart moving to the left, but with a small velocity. And we'll have the red cart moving to the right, but with quite a big velocity. Then again, let's try to subtract these arrows. So you see, you take this arrow minus nothing, and you get something that points that way. And then you take this arrow minus that arrow, it's like that. See, it's kind of like that. And then the reverse of that initial arrow, which points to the left, would be something like that pointing to the right. So again, we'll have a big change in velocity to the right for the red cart, the lightweight cart, and a small change in velocity to the left for the blue cart, the more massive cart. So let's watch that. Let's look at one more version of the collisions between a blue cart of 3 units of mass and a red cart of 1 unit of mass. So the blue cart has 3 times the mass of the red cart. I am going to send them toward each other with roughly the same speed. The blue cart is moving to the right and the red cart is moving to the left. the speeds I'm going to try to match as well as I can with my hands. You get kind of an interesting result here. It will turn out that the blue cart will stop dead in its tracks, and the red cart will recoil with an outgoing velocity that is 2 times the magnitude of its incoming velocity. So we start out with 1 unit to the left, and we go out with 2 units to the right. And here we come in with 1 unit to the right, and we go out with 0. So this minus this is a change that looks like that. This minus this, so to subtract that, we put this on the end. That's a change that looks like that. So this change has 3 times the magnitude of this change. So I think that makes sense, since this mass is 3 times as big as this mass. So if this velocity change is 3 times as big as this velocity change, then because of the ratio of masses, this momentum change is the same in magnitude as this momentum change, but of course they're in opposite directions. So this is 3 units of velocity change to the right for the red cart. This will be 1 unit of velocity change to the left for the blue cart, although equivalently the momentum changes are the same magnitudes and opposite directions. So let's see what that looks like. Now let's go back to equal masses and let's watch a different kind of interaction. Let's watch the 2 carts push away from each other. So it's kind of like if you and I are both on roller skates and we start out with our hands kind of clasped like this and push against each other. So what's actually going to happen is I have the blue cart here, the red cart here. Each one has 1 unit of mass, and there's a little coiled up spring in between them. And then we release that little coiled up spring. We'll see how that works a couple chapters from now. The result of releasing the coiled up spring is that the 2 carts push away from one another. And because they have the same masses, and initially they both have 0 momentum, the 0 velocity, therefore 0 momentum, and the total of the 2 momenta is 0 initially. So each cart is not moving, the system is not moving. So initially V1x initial is 0, V2x initial is 0. They push away from each other. So if the red cart moves to the right with 1 unit of velocity, then to conserve momentum, the blue cart moves to the left with 1 unit of velocity. So this final blue arrow points to the left and it's 1 unit long, and this final red arrow points to the right and it's 1 unit long, representing the 2 velocities. So that's a change in velocity. So this minus 0, so this is the initial state here, and this is the initial state here. This is kind of like a motion diagram, by the way. The last time I think I told you that motion diagrams weren't very useful to me. This is kind of a motion diagram. So here's time 0, and I'm showing them not moving, and here's some later time, and I'm showing them moving away from one another. That's about as fancy as my motion diagrams get. This final minus initial looks like this for cart 1, the blue cart, and final minus initial looks like this for cart 2, the red cart. So you can see that m1 times delta v1 plus m2 times delta v2, they add up to 0. So you can also see the ratio of these 2 changes in the x direction in velocity is -1, since m2 over m1 is 1. Let's see what that looks like. Let's look at the same thing now for the case where we add an extra unit of mass to the blue cart. So now the blue cart is 2 units of mass, the red cart is 1 unit of mass. They both start out at rest and they're connected by a compressed spring, and then I release the spring and they push apart from one another. So the change in velocity of the blue cart will be -1/2 the change in velocity of the red cart, since the blue cart has twice the mass of the red cart. And they both start out at 0. In the final state, the blue cart's velocity will be this little arrow to the left, and then twice as big as that to the right will be the red cart's velocity. So if the red cart has 1 unit of velocity to the right, then the blue cart has a 1/2 unit of velocity to the left. So delta v1x looks like this little arrow to the left, and delta v2x looks like this big arrow to the right. Then let's see what that looks like. If I make the red cart twice as massive as the blue cart, then you can hear them reach the ends at different times. What if we make the distances that they have to travel a ratio of 2 to 1? So you see the blue cart will have to travel twice as far as the red cart will to hit the end. Then I think your ear will detect that they hit the ends at the same time. Let's see how that goes. Yeah. So you can see the blue cart travels twice as much distance as the red cart does after they separate, which confirms the idea that the speed of the blue cart is twice the speed of the red cart after they separate. I'll bet you guessed what's coming next, so let's do the same thing now, but with a 3-to-1 ratio of mass. So we've now tripled the mass of the blue cart by loading 2 little bricks into its little payload area. 3 units of mass for the blue cart, cart 1. 1 unit of mass for the red cart, cart 2. They start out both at rest. They're squished. They have a squished together spring, so they're going to push apart. So the change in velocity for cart 1 in the x direction will be -1/3 the change in velocity of cart 2 in the x direction, since they both start out at 0. So the final velocity of the blue cart will be this little arrow, let's say 1 unit long, to the left, and the final velocity for the red cart will be this big arrow, let's say 3 units long, to the right. So then this -0 is like that, and this -0 is like that. And again, if you multiply this by its mass, and you multiply this by its mass, then you have 2 arrows that sum to 0. In other words, the changes in momentum sum to 0. Let's watch that. And then we can make the ratio of masses be 3 to 1. So the red cart will be 3 times the mass of the blue cart. And then we can position them in such a way that the distance that the red cart has to travel is 1/3 of the distance that the blue cart has to travel. And let's try that. That's pretty good. Not bad. Okay. So now that we've gone through those examples of collisions between objects sometimes of the same mass, sometimes of a ratio of masses of 2 to 1 or 3 to 1, and in every case it's been an isolated system of 2 objects interacting only with each other. That was on the little rolling carts on a track. You will actually do something very similar with little rolling carts on a track in class after we've gone through chapter 5. So this will be chapters 4 and 5 together. Meanwhile, let's move on to the air track. That's just like the air hockey table. And the air track will not be tilted this time. It will be a level air track. So we're going to have a level air track. We're not studying acceleration anymore. Now we're studying momentum. So the air track will be level. We're going to collide pairs of carts on the air track, and we're going now to look at graphs of velocity versus time for cart 1 and for cart 2, and sometimes their masses will be the same and sometimes they'll be different. So we're going to go through an exercise very similar to what we just did a moment ago, but we're going to use graphs of the initial state and the final state and see if we can understand which graphs make sense to describe the motion of the 2 carts. To be a bit more quantitative about pairs of carts colliding, I've made some graphs, and I've combined them with some video clips of the air track, which is basically like an air hockey table. What we're going to see in the clip is cart 1 will initially be moving to the right, and cart 2 will initially be stationary. They're going to collide, and after they collide, cart 1 stops dead in its tracks. Cart 2 continues with an outgoing velocity that equals cart 1's incoming velocity. If you like to play pool, that's exactly what you see when you hit a stop shot. We want to look for graphs that match the initial conditions and also match our observations. Let's first pause and watch the clip. Yeah. It seems as if graphs A and C are not compatible with what we see in the clip, because they seem to represent an initial state where the 2 carts are moving toward one another, and that's not the initial state we have. The initial state we have is where cart 1 is moving toward a stationary cart 2. By the way, each one of these graphs has the x component of velocity on the vertical axis, and I've tried to label key features here, like here's -1 meter per second, here's +1 meter per second, here's -1 meter per second, here's +1 meter per second. And then there's time on the horizontal axis. And if you want to see these graphs more clearly, you can look at the PDF slides at phys0008 slides.04.pdf in the course files area. For 2 carts of equal mass colliding, we expect the change in velocity in the x direction for cart 1 to be the same magnitude but the opposite sign as the change in velocity in the x direction for cart 2. Delta v1x over delta v2x is minus m2 over m1, which is -1 if the 2 masses are the same. Then we can look at the graphs. And let's look at graph B here. Cart 1 goes from +1 meter per second to -0.3 meter per second. That's a change of -1.3 meter per second. Cart 2 goes from 0 meter per second to +0.7 meter per second. That's a change of +0.7 meter per second. The changes do indeed have opposite sign, but the velocity change for cart 1 is twice as big, within rounding, as the change for cart 2. That would only make sense if cart 2 had twice the mass of cart 1, but we said that the 2 carts have the same mass, so we can rule out B. Graph D looks like our best fit. Cart 1 goes from +1 to 0 meter per second. Cart 2 goes from 0 to +1 meter per second. So cart 1 has a change of -1. Cart 2 has a change of +1. That makes sense. They have the correct ratio of -1. It's also consistent with what we saw in the video clip. So I like D, delta. Let's watch the clip one more time. Let's look at a second example with that same combination of masses. So the 2 carts are equal mass, but now they will initially be moving toward one another, like that. Cart 1 is moving to the right initially. Cart 2 is moving to the left initially. Let's see which of these graphs match those initial conditions. Graph B does not, because it shows cart 2 initially stationary. Graph D seems to match the initial conditions. Graph C does not match the initial conditions. It has cart 2 initially stationary. So it's either A or D. Let's work out what we think we expect. This seems like a change of -2 units, from +1 to -1 meter per second for cart 1. For cart 2, it looks like a change of +2 units, from -1 to +1 meter per second. So the ratio of changes in velocity in the x direction is correct. It's -1, which equals the ratio -m2 over m1. Let's look at graph D and see if it makes sense. Cart 1 goes from +1 to -1.7, so that's a change of -2.7 meter per second. Cart 2 goes from -1 to +0.3 meter per second, a change of +1.3 meter per second. A change of +1.3 versus -2.7, which would be correct only if cart 2 had twice the mass of cart 1. But we're told that the 2 carts are equal mass, so we can rule out D. So what we expect to see is that after the collision, cart 1 will be moving to the left, and cart 2 will be moving to the right. The 2 carts will essentially just trade velocities. Let's watch the clip. It does seem from the clip that the 2 carts did, in this case, basically just trade velocities. It turns out that's what happens when you have a direct hit between 2 objects of equal mass if, as we'll see in the next reading assignment, no energy is lost in the collision. Next time we'll call that an elastic collision. We did see that the 2 carts basically traded velocities. That's consistent, again, with graph A, alpha. For our next example, let's look at a collision between carts of different masses. Cart 2 will be twice the mass of cart 1. I drew cart 2 bigger than cart 1 to make it visually obvious. Cart 1 initially is moving to the right. Cart 2 initially is stationary. What do we expect after they collide? Let's see if we can rule out any of these graphs. Cart 1 initially moving to the right, cart 2 initially stationary, could be A, cannot be C because it doesn't match our initial conditions. A, B, and D match the initial conditions. We can rule out C. If we look at A, cart 1 goes from +1 to +0.3, a change of -0.7 meter per second. Cart 2 goes from 0 to +1.3 meter per second, a change of +1.3. Within rounding, -0.7 versus +1.3 is a ratio of -2, but it's in the wrong direction. This is what you would expect if cart 1 were twice the mass of cart 2. We can rule out A. Let's look at B. Cart 1 goes from +1 to -0.9, a change of -1.9 meter per second. Cart 2 goes from 0 to +0.2 meter per second. That's a ratio of -10. That would make sense if cart 2 were 10 times as massive as cart 1. Cart 2 is more massive than cart 1, but not by a factor of 10. It's only a factor of 2. Let's look at D, delta. Cart 1 goes from +1 meter per second to -0.3 meter per second, a change of -1.3 meter per second. Cart 2 goes from 0 to +0.7 meter per second, a change of +0.7. Within rounding, that makes sense. The change in velocity for cart 1 is twice the magnitude of the change in velocity for cart 2, and of course they're in opposite directions. That makes sense because the less massive cart should experience twice as large in magnitude a change in velocity. If we want to draw the final state here, what this depicts is in the final state, cart 1 recoils backward, so it's going about 1/3 as fast backward as it was initially going forward. And cart 2, initially at rest, is now going at something like 2/3 the speed at which cart 1 was initially going. Let's look at the clip and see if it resembles this picture. So we will take some little masses and put them onto the red cart. So now we've doubled the mass. I think the clip does look like this picture. That's pretty good. In the final state, cart 1 is going backwards. Maybe about 1/3 the speed it was initially going, but in the opposite direction. And cart 2 is now going to the right, but with a final speed that is maybe 2/3 of the initial speed of cart 1. By the way, for this collision that we just watched, where cart 2 has twice the mass of cart 1, and cart 1 is initially moving to the right, and cart 2 is initially stationary, the graph that we chose was this graph. Now it's drawn bigger. Here's the x component of velocity measured in meters per second on the vertical axis. Here's the time measured in seconds on the horizontal axis. Cart 1 went from +1 meter per second down to -0.3 meter per second, and cart 2 went from 0 meter per second up to +0.7 meter per second. You can see the change in the yellow curve has twice the magnitude of the change in the blue curve. So the change in velocity for cart 1 had twice the magnitude, and of course opposite direction, of the change in velocity for cart 2. And that makes sense. It's minus the ratio of the two masses. The question is, if we drew momentum on the vertical axis instead of drawing velocity on the vertical axis to describe this collision, would the yellow and blue curves have this ratio of changes that's different from 1? Or would the change in momentum for the first cart be the same magnitude as the change in momentum for the second cart? Think about that, and I'll show you the graph on the next page of momentum instead of velocity on the vertical axis. Looking instead at a graph of momentum versus time instead of velocity versus time, so we have the x component of momentum on the vertical axis, and momentum has units kilogram meters per second, and we still have time on the horizontal axis. We see cart 1 goes from +1 kilogram meter per second down to -0.3. That's a change of -1.3 kilogram meter per second. And cart 2 goes from 0 up to +1.3. That's a change of +1.3 kilogram meter per second. Cart 1 experiences a change of -1.3. Cart 2 experiences a change of +1.3. The two changes are equal and opposite. That makes sense. The momentum lost by cart 1 equals the momentum gained by cart 2. The sum of the two momenta is the same before and after the collision. This is what you expect from the collision of two objects that form an isolated system. In other words, the collision of two objects that interact only with one another. The total momentum before equals the total momentum after. Therefore, the change in momentum of one cart must be offset by the change in momentum of the other cart. So the two changes must sum to 0. And then you can see where the average of these two curves is. If you take the average and double it, you get the sum. We know that the sum of the two curves is the same before and after colliding. It's easy for your eye to notice that the average of the two curves is the same on the left as it is on the right. The average is just 1/2 of the sum. Again, the change in p sub x for cart 1 is negative. The change in p sub x for cart 2 is positive. Those two changes have the same magnitude. Because momentum is a conserved quantity, and because this is an isolated system. Therefore, momentum is constant for this system. Now let's consider a collision between the same two carts. Cart 2 has twice the mass of cart 1, but initially cart 2 is moving to the left while cart 1 is stationary. Let's see which graphs match those initial conditions. Cart 1 should be stationary. Cart 2 should be moving to the left. B matches those conditions. And A matches those conditions. C also matches those conditions. D does not, because D shows cart 1 moving to the right and cart 2 moving to the left. So it's A, B, or C. We know the ratio of changes in velocity should be minus the reciprocal of the ratio of masses. If we look at A, cart 1 goes from 0 to -0.7 meter per second. Cart 2 goes from -1 to +0.3. That's a change of -0.7 and a change of +1.3. That's a 2-to-1 ratio, but it's in the wrong direction. Having the more massive cart experience a larger change in velocity doesn't make sense. If we look at B, cart 1 undergoes a change of -1.3 meter per second. That's from 0 to -1.3. Cart 2 undergoes a change from -1 to -0.3, so that's +0.7 meter per second. That's +0.7, that's -1.3. That's a 2-to-1 ratio in the correct direction, so I like B. Bravo. We're pretty sure we like B, but let's just look at C to be sure. Cart 1 goes from 0 to -1.8 meter per second. That's a change of -1.8. Cart 2 goes from -1 to -0.8 meter per second. That's a change of +0.2. That would be a 9-to-1 ratio of masses. This is what you would see if cart 2 were 9 times as massive as cart 1. Cart 2 is more massive than cart 1, but it's not 9 times as massive. So we rule out C, and we still like B. What B would look like in the final state is cart 1 is moving backward, and it's moving backward faster than cart 2 initially was moving. So cart 1 will be moving to the left at a bigger speed than cart 2 was initially moving to the left. Cart 2 will also be moving to the left, but with about 1/3 of its initial speed. Cart 2 should continue moving to the left, but its final speed should be about 1/3 of its initial speed. Cart 1 should be moving to the left with a speed that is a little bigger than cart 2's initial speed. That seems to be a way for us to conserve momentum when cart 2 has twice the mass of cart 1, where cart 2 is initially moving to the left and cart 1 is initially stationary. Now let's watch the clip. Again, I think the clip matches graph B. The next example will use the same two carts. Cart 2 has twice the mass of cart 1, but now they start out moving toward one another with similar initial speeds. Let's see what we expect. Let's look at the graph's initial conditions. +1 and -1 for B, +1 and -1 for A, +1 and -1 for C, +1 and -1 for D. They all seem to match the initial conditions, so we can't rule anybody out that way. The change in velocity for cart 1, the less massive cart, should be twice the magnitude, and of course in the opposite direction, of the change in velocity for the more massive cart. Let's see what we have in the graphs. If we look at A, we go from +1 to -0.3, a change of -1.3. Here we go from -1 to +1.7, a change of +2.7. That's a factor of 2, but cart 2 has a bigger change than cart 1 in magnitude. That doesn't make sense. The more massive cart should have the smaller magnitude change in velocity. Let's look at B. Cart 1 goes from roughly +1 to -2 meters per second, a change of about -3. Cart 2 goes from -1 to -0.2, a change of about +0.8. That would be roughly a 4-to-1 ratio of mass, so it does have cart 2 more massive than cart 1, but by a ratio around 4-to-1, which is not consistent with our problem statement. Then we can look at C. There's +1 down to -1 is a change of -2. Then -1 up to +1 is a change of +2. C is what we would expect if the two carts had equal mass. They do not have equal mass. Let's look at D. +1 down to -1.7 is a change of -2.7. Then -1 up to +0.3 is a change of +1.3. So this is -2.7 and +1.3. Within rounding errors, that makes sense. The change is twice as big in magnitude for cart 1, the lighter cart. Half the magnitude for cart 2, the more massive cart, by a factor of 2. In the final state, cart 1 is going backwards, with almost twice its initial speed, so it really recoils backwards. And in the final state, cart 2 is going forward. That's to the right, with about 1/3 its initial speed. So it's something like that. Let's watch the video clip. Okay, so I think that's what we saw, consistent with D, delta. We went from +1 to -1.7 with cart 1, and cart 2 went from -1 to +0.3. So the change in velocity for cart 1 had twice the magnitude of the change in velocity for cart 2, consistent with cart 2 having twice the mass of cart 1. Which has more momentum? An 0.5 kilogram baseball pitched at 40 meters per second, or an 0.01 kilogram bullet fired at 400 meters per second? Okay, so a half kilogram baseball versus a 10-gram bullet, but there's a factor of 10 ratio of velocities. Let's work that out. Momentum is what times what? Momentum is mass times velocity. Here we just want the magnitude. So the magnitude of the momentum is the mass times the speed. The bullet is going 10 times as fast as the baseball, but the baseball has 50 times the mass of the bullet. So I think the baseball is going to have the larger momentum. Let's see. For the baseball, P is mv, which is 0.50 kilograms times 40 meters per second, which is 20 kilogram meters per second. And for the bullet, we have 0.01 kilogram times 400 meters per second, which is 4 kilogram meters per second. So indeed, the baseball has the bigger momentum. One way to measure the speed of a bullet is to fire the bullet at a wooden cart of known mass, which is initially at rest, and then to measure the speed of the cart with the bullet embedded in the cart. The figure shows a 0.01 kilogram bullet, that's a 10-gram bullet, fired at a 4 kilogram cart. After the collision, the cart rolls to the right at 2 meters per second. What is the bullet's speed before it strikes the cart? The key here is that the bullet plus cart system is isolated. Along the x-axis, the bullet and the cart interact only with each other. That's at least a true statement in the horizontal coordinate. So the total momentum of the bullet plus cart system before colliding equals the total momentum of the bullet plus cart system after colliding. And then there's a very convenient fact here, which we'll explore in more detail in Chapter 5. Since the bullet and cart collide and stick together after the collision, the velocity of the bullet and the velocity of the cart are equal, because they stick together and are moving together afterward. That makes life easy for us. Here's the initial state, with a textbook-style clock. Let m equal 0.010 kilogram, that's the bullet. Then let big M equal 4 kilograms, that's the cart. Come to think of it, let's do as our book would do, and let the bullet be object 1, and let the cart be object 2. v1x initial is unknown, and v2x initial is 0. The bullet is moving to the right at some large unknown speed. The cart is at rest. In the final state, we have the bullet and the cart together, with a velocity that we expect to be much smaller than the bullet's initial velocity. We have v1xf equals v2xf equals 2 meters per second. Let's use the momentum equation. This is the equation we'll use for all problem solving with momentum when we have just two objects colliding along the x-axis. m1 v1xi plus m2 v2xi equals m1 v1xf plus m2 v2xf. In this case, the equation simplifies right away because object 2 initially is not moving, so that term is 0. Also, the final velocities are the same. Let's give that a name. Call it vxf. It's the same final velocity for both objects. m1 v1xi equals m1 plus m2 vxf. I'll make the second m big since the diagram did. Now we just divide both sides by m1 and we're done. v1x initial, the initial x component of the velocity of the bullet, equals m1 plus m2 over m1 times vx final. Plugging in numbers gives 802 meters per second. Answer D, delta. That's our first quantitative problem using momentum. Isn't that fun? A final exam problem used in this course several years ago started out like this. You have been hired to check the technical correctness of an upcoming made-for-TV murder mystery. The mystery takes place in a space shuttle. Oh gosh, there used to be a space shuttle. In one scene, an astronaut's safety line is sabotaged while she is on a spacewalk, and she is no longer connected to the space shuttle. She checks and finds that her thruster pack has also been damaged and no longer works. She is 200 meters from the shuttle and moving with it. That is, she is not moving with respect to the shuttle. There she is, drifting in space, with only 4 minutes of air remaining. To get back to the shuttle, she decides to unstrap her 10-kilogram toolkit and... what does she do with it? What does she do with her 10-kilogram toolkit? Now that you are an expert at momentum, you know that she should throw her 10-kilogram toolkit with all her might. Now, she wants to move herself toward the space shuttle. So which way should she throw her 10-kilogram toolkit? I think she should throw her 10-kilogram toolkit with all her might away from the space shuttle. Then she will recoil toward the shuttle. Then we'll need to evaluate whether she can throw her toolkit away from the shuttle with a large enough velocity that her own recoil velocity is then fast enough to get her back to the shuttle within 4 minutes. We can reason that this is a momentum problem, so we could set up the problem by saying Object 1 is the astronaut, Object 2 is the toolkit, m1 v1xi plus m2 v2xi. Initially neither one is moving, so both terms are 0. Then that equals m1 v1xf plus m2 v2xf. Initially this is 0 and this is 0. So the astronaut's final velocity in the x direction is v1xf equals minus m2 over m1 times v2xf. Presumably the rest of the problem gave us her mass, including her spacesuit, and the speed at which she throws the toolkit. The toolkit is 10 kilograms. Let's say the astronaut, with spacesuit but without toolkit, is 70 kilograms. And then this is however fast she throws the toolkit. And then this is her final velocity toward the space shuttle. So with these numbers, whatever speed she throws the toolkit away from the shuttle, she recoils toward the shuttle at 1/7 that speed. That's the idea. Then you'd have to work out whether she makes it back within 4 minutes, traveling at constant velocity toward the shuttle. So this equation gets us quite far in Chapter 4. In the old days, this problem was a segue into a demonstration you already saw, in which two carts initially at rest, with a compressed spring in between them, fly apart when the spring is released. So I'll just show you again, for fun, that demo for a 3-to-1 ratio of mass, even though we probably expect more like a 7-to-1 ratio in this problem. Then we'll move on. There are several things that Eric's book does really well in this chapter. One of them is introducing the concept of a system, and another is introducing the concept of a conserved quantity. It turns out that all conserved quantities in physics are extensive quantities. There are some extensive quantities that aren't necessarily conserved, but all conserved quantities are extensive. What is an extensive quantity? This is kind of a detail. You don't really need to know what an extensive quantity is, but students often ask about this. By explaining this, Eric is helping you to gain intuition about the use of conserved quantities in physics problems. A quantity Q describing a system is extensive if, when you divide up the system into two parts, Q of part 1 plus Q of part 2 equals Q combined. For instance, money in the bank has this property. If you divide up your cash into two parts, where one part goes into your checking account and the other part goes into your savings account, and you say, what's my combined amount of money? It's the money in account 1 plus the money in account 2. A lot of things have this property. The mass of stuff. It's often true with the volume of stuff, but that can sometimes not be true if, for instance, there's a chemical reaction that causes volumes to change if they're combined in a beaker. But it's usually true with volume. I have a room of so many cubic meters. I have another room of so many cubic meters. What's the combined volume? It's just the sum of the two volumes. Money is extensive, but not conserved. You have two amounts of money, and you say, how much is the total? You just add the numbers together. But the Treasury could print money, or you could burn a pile of dollar bills, so money is not a conserved quantity. Number of atoms is an extensive quantity. I have n atoms in one box and I have m atoms in another box. The number of atoms combining the two boxes is n plus m, but it's not necessarily conserved if you can have fission or fusion of nuclei. Some counterexamples, things that are not extensive quantities. Humidity. Say there's 30% relative humidity in the hallway and 80% relative humidity in the bathroom where someone just showered. I'm not going to open a door and say the combined humidity is 110%. That doesn't make any sense. Density. I have some water. Density 1 gram per cubic centimeter. Then I have some rock. Density 2.3 grams per cubic centimeter. Then I put the rock into the water. I don't have 3.3 grams per cubic centimeter. That just doesn't make sense. Temperature. I have one object at 50 degrees Celsius and another object at 60 degrees Celsius. If I combine them, I don't get 110 degrees Celsius. Some extensive quantities are conserved, only a few. A quantity which is conserved can be transferred from one object to another, but can never be created or destroyed. Momentum, and then in Chapter 5, energy, are examples of conserved quantities in physics. All conserved quantities are extensive, but only a few extensive quantities are conserved. If this really confuses you, don't worry about it. We discuss it here to build up intuition about conserved quantities and systems. A few examples may help. For instance, how about number of dots? Is number of dots an extensive quantity? I think so. Look, I've got this many dots on the left, say 10. I've got, let's say, 15 dots here. I say, what's the total number of dots? It's 25 dots. I'd say yes for dots. How about dot diameter? Here I have a dot diameter of 1. Here I have a dot diameter of 1. If I combine the two pictures, do I have a dot diameter of 2? No. Dot diameter is not an extensive quantity. How about total area covered by dots? Well, if I add up the total area covered by dots over here, and I add up the total area covered by dots over here, I think I can add those, and I get the total area covered by dots. That seems fine, though if you want to be really careful, you'd say, well, yes, as long as the dots don't overlap. You see, if I take these dots and overlay them on these dots, if some of them overlap, then that might cause the total area covered by dots to be different from just adding the two areas. But if you leave out that possibility, I'd say yes, as long as the dots can't overlap. You see? This is sort of a digression, but it may be relevant for one upcoming worksheet question. Just one little part of one worksheet question. There's an example of a velocity versus time graph. The velocity versus time graph below shows the motion of two different objects moving across a horizontal surface. Could the change in velocity versus time be attributed to friction in each case? We don't know anything about friction yet in this course, really. Except, we know that friction tends to slow down the motion of an object with respect to the surface on which it's sliding. That's all we know at this stage. This is 0. Here's velocity. Here's negative velocity, and here's positive velocity. The x component of velocity, that is. And here's time. We have time on the horizontal axis. We have the x component of velocity on the vertical axis. Consider friction for something sliding across a surface. I have a surface here. Then I have an object which is moving. What does friction do? It makes the object slow down. Whether it's moving right or left, friction causes it to slow down. Friction reduces the speed. It reduces the magnitude of the velocity. What's happening here? Is this object speeding up or slowing down? Its speed seems to be getting bigger. The magnitude of its velocity is getting bigger, so this cannot be due to friction. Friction would not cause something to speed up unless maybe you drop an object onto a moving conveyor belt and the object slides until it catches up to the speed of the conveyor belt. But if it's sliding on a stationary horizontal surface, friction will not cause it to speed up. What about here? This object seems to be slowing down. See, it's moving backwards, and now it's moving backwards less quickly, and now it's moving backwards less quickly, moving backwards even less quickly. Eventually it's going to stop. So this is slowing down, whereas this is speeding up. So friction is not going to cause something to speed up except in a weird case like dropping it onto a conveyor belt and it catches up to the conveyor belt. Friction will cause something to slow down. It will not cause something to speed up. So I would say no for the top curve, yes for the bottom curve. That's B, bravo. Now, when we study friction carefully in Chapter 10, we will see the type of friction that speeds you up when you walk, or that accelerates your car. The idea in this graph is that for an object sliding across the ground, friction will slow that object with respect to the ground. Here are the key results from Chapter 4, the momentum chapter. Momentum is mass times velocity. Velocity is a vector. Mass is a scalar. If you take a vector and multiply it by a scalar, you get another vector. So momentum is a vector which points in the same direction as velocity since m is greater than 0. The units of momentum are kilogram meters per second. The units of velocity are meters per second. The units of mass are kilograms. So you multiply velocity by mass, the units you get are kilogram meters per second. In one dimension, we'll just deal with the x component. P sub x is m times v sub x. The x component of momentum is the mass times the x component of velocity. You'll see Eric say inertia when he writes m for mass. Inertia is mass. If you have an isolated system of two objects, that means two objects that interact only with each other and not with anything else. You can say the total momentum in the x direction before the interaction equals the total momentum in the x direction after the interaction. Mass times velocity in the x direction plus mass times velocity in the x direction for the initial state equals that same sum for the final state. When you solve problems using momentum, as we'll do in worksheet 4, you'll write down this equation probably half a dozen times. m1 v1x initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. If you define delta v1x to be v1x final minus v1x initial, and you define delta v2x to be v2x final minus v2x initial, and you solve for delta v1x over delta v2x, you get minus m2 over m1. This first version is useful for problem solving. This second version is useful for looking at those graphs of two things colliding and seeing what makes sense. The ratio of the two changes in velocity should be a negative number because they should be in opposite directions, and that's the reciprocal of the ratio of masses. If you happen to have a non-isolated system, and if you happen to know how much momentum enters or leaves the system across the system boundary, then the final momentum minus the initial momentum of a system, due to some interaction, is given this symbol J for impulse in Eric's book. But we will almost never quantify impulse except to be able to argue that it equals 0. If no momentum enters or leaves the system, which is true if you have an isolated system, in other words, the constituents of the system interact only with one another and not with anything outside the system, then the total final momentum of the system equals the total initial momentum of the system. So P final minus P initial is 0, 0 impulse. Pretty much the only time you'll use impulse is just to say that it equals 0 for a system that is isolated. But it's in the book, so I want to mention it. By the way, at this stage, do you remember the key results from Chapter 3 on acceleration? They might be worth writing down. See if you can remember them with me. The small number of key results from Chapter 3, acceleration, that are worth remembering. The first one, which is really from Chapter 2, v sub x is dx by dt. The x component of velocity is the rate of change of the x coordinate. Then a sub x is dv sub x by dt. The x component of acceleration is the rate of change of the x component of velocity. I could also say that a with a vector arrow is the time derivative of v with a vector arrow, but let's not do that. If a sub x is constant, then we have vx final equals vx initial plus a sub x t. X final equals x initial plus v sub x initial times t plus 1/2 a sub x t squared. Then if you solve this equation for t and then plug that t into this equation, what you get is vxf squared equals vx initial squared plus 2a sub x times x final minus x initial. Two other useful chapter 3 results are that for free fall near Earth's surface, we have the x-axis pointing up, and we have a sub x equals minus g. Then for sliding with negligible friction down an inclined plane, we have the x-axis pointing downhill, and a sub x is plus g sine theta, where theta is the incline angle with respect to the horizontal. Those are all the key results from chapter 3. And then this and this are really the only two key results from chapter 4. Also this definition. By the way, we're going very quickly through the early chapters of Mazur's textbook. Chapters 1 through 9 go pretty quickly. We're going to slow down for the more difficult topics. Chapters 10, 11, 12 will be the most difficult part of the course, so we'll take a lot more time per chapter when we get there. One reason for the faster pace now is to leave time for the fun stuff at the end. Once we get through Mazur's chapter 12, which covers torque, we can take our knowledge of vectors, forces, and torques, and use them to learn some things about architectural structures. I hope that's one of the key features that make this course fun. Next, we have one more example problem if you want to see a bit more on how we're going to solve problems using momentum. Here's an example problem that I'm writing out from memory. The classic problem is two male moose of different masses, a big moose of mass m1 and a small moose of mass m2. And they're charging one another on a sheet of icy tundra. Why is it icy tundra? Icy so that we can say that friction is negligible. So then we can say there's no horizontal interaction with the ground, so the moose plus moose system is an isolated system along the x-axis. Two male moose charge in opposite directions toward one another at the same speed but in opposite directions on an icy patch of tundra. In the initial state, we have a big moose moving to the right with speed v initial. We have a little moose moving to the left with speed v initial, but of course the corresponding velocities are in opposite directions. Then their antlers lock together, and this tangle of moose and arms and legs and antlers goes sliding together across the tundra. Which direction does it slide? This moose has a bigger momentum to the right compared to this moose's momentum to the left. This moose's momentum to the right is bigger than this moose's momentum to the left, because it's the same speed, but the big moose has a bigger mass. So the total momentum of the moose plus moose system points to the right in the initial state. Therefore, the total momentum of the moose plus moose system will point to the right in the final state. In the final state, the moose's antlers are locked together, so the two mooses move at the same velocity, the same v final. They're locked together. They move together. In the real problem, you know the final speed, and you solve for the ratio of the masses. I'm going to change it up here. Let's say that m1 equals 2 m2, and we want to know what is v final compared to v initial. Let's say v initial is 10 meters per second. Then what is v final? The total final momentum equals the total initial momentum because the two moose system is horizontally isolated. We only care about the x-coordinate. Along the x-axis, the two mooses interact only with each other and not with anything else because the ground is slippery, so there's no friction. We can write m1 v1x initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. Taking the x-axis to point to the right, we know that v1x initial equals plus v sub I. v2x initial is minus v sub I. v sub I is just the speed, so v1x initial is plus 10 meters per second, v2x initial is minus 10 meters per second. We also know that m1 is 2 m2. Plugging that in, m1 minus m2 v initial. Then we also have v1x final equals v2x final equals v final. We'll just call that v final. This is m1 plus m2, v final. That's enough to solve for v final. V final is m1 minus m2 over m1 plus m2 times v initial. That works out to be plus 1/3 v initial, which would be plus 3.3 meters per second. You have a big moose, 2 units of mass, moving to the right at speed v. You have a little moose, 1 unit of mass, moving to the left at that same speed v. They collide, their antlers lock. Now they slide together on the icy tundra. The total momentum afterward is the same as the total momentum before. So then you can work out that the speed at which the two moose system slides after their antlers lock for this ratio of masses is 1/3 of this initial speed of each moose. So if the initial speed of each moose going toward the other is 10 meters per second, then after colliding, the two moose system slides to the right, which is the initial direction of the bigger moose, at 3.3 meters per second. I think you'll solve a similar problem where you're told the final speed and you have to figure out the ratio of the two masses. So there's one more example of a quantitative problem you can solve with momentum. At this stage, since we haven't covered energy yet, for most of the problems we can solve, either the two objects stick together, or maybe you're given both initial velocities and one of the two final velocities, and you have to solve for the other final velocity. With the momentum equation, if you only know the initial state, then the final state has two unknowns, and you only have one equation. Next chapter, energy will give us a second equation. Having the two objects stick together eliminates the need for a second equation. You can ponder that, and I'll see you in class for worksheet number 4.